to thank the organizers for inviting me to present our work here. Now I will somehow present ongoing work with Ellie Wolf at Perimeter Institute that builds up on our previous work on contextuality with Tony Yassine, Tobias Fried, and Anthony Leverrier. So at the very beginning, I will somehow review our formalism for contextuality and then move on to the composition bit of the talk. So a contextuality scenario, the way that we visualize the setup of the experiment, so to say, is we have a system where we can perform measurements and obtain outcomes. So that is the setup that you have to keep in mind throughout the whole talk. Of course, if I just stop here and this is all I give you, you'll be a bit disappointed because this is somehow trivially boring. It's not like yesterday when we had this example of the particle in the box that was the simplest thing that we could have and still it was interesting. This is somehow trivial. So what we do to make it more interesting is to identify different outcomes of different measurements. So that's the setup that you must have in mind. And what do I mean by this? Let's suppose, and let me depict the situation in this way, that we have two different measurements. So each of these ellipses is a measurement, and each of them has three outcomes, and the outcomes are depicted by these dots there. It might happen that we perform these measurements on our system, and we check, or we actually see that for all the possible preparations of the system, these two outcomes there always happen with the same probability. And if that's the case, then we will identify those two outcomes, or say that those two outcomes correspond to actually the same event, and then we will have a situation like this. So now we will have two different measurements, but some of their outcomes have been identified. This might seem somehow a little bit like imposed with no physical grounds, but this is actually something that arises naturally within quantum theory, even though quantum theory is not what we want to assume throughout the talk. For instance, in quantum theory, actually a measurement is a realization of the identity. So it's basically a sum of positive operators that give you the identity. And if it happens that the operator that is associated to this outcome here is the same one that you associate to the other outcome, then you will always obtain the same probability, regardless of which is the density matrix of the system that you're performing your measurements on. So basically that's what we have in mind when we say, well, two different events can be identified as being the same one. So our formalism for contextuality basically takes as a starting point the set of measurements that you can perform on your system and the identifications among the different outcomes of the measurements. And a very useful way to depict such a situation is via a hypergraph. So a contextuality scenario basically is given by a hypergraph where the vertices are the possible measurement outcomes that you can obtain in the experiment, and the hyperedges contain all the outcomes for each of the measurements. And from here on, we will assume that the measurements are complete. So every time that you perform a measurement, one of the outcomes of that measurement must occur. So given that we have this situation here, so this contextuality scenario, the object that we're interested in studying are conditional probability distributions. That is, the assignment of values between 0 and 1 to each of the vertices such that that value represents the probability that such an outcome occurs whenever the measurement is performed. For instance, this one here is a possible assignment of probabilities to this particular hypergraph that I depicted. And the set of all the possible probabilistic models that satisfy these normalization constraints, because we would like the probabilities to sum up to 1 for each of the hyperedges, is what we call the set of general probabilistic models. And they actually form a polytope. But now this is like a very general way of looking at the situation. So in practice, we have now in the labs classical systems or quantum systems. So we would like to see what happens if we further assume that the nature of the system that we are acting on is either classical or quantum. So in the case where it's classical, then the possible probabilities that may arise are those that are compatible with a local hidden variable model, so to say, or a non-contextual hidden variable model. So basically are those where the probabilities are just a linear combination of deterministic models on the hypergraph. For instance, this one here is actually a deterministic model. And when that happens, then the possible probabilistic models that may arise in the experiment is just a subset of all the possible ones that we would have otherwise. But now, if we want to assume that the system is a quantum system and that we perform measurements on it, what actually, the way that we model this is, well, an assignment of probabilities will have a quantum nature, a quantum realization, if there exists a Hilbert space and a state for the system and measurement projectors for each of the outcomes such that the probabilities are recovered via the Born rule. And of course, since we are working with complete measurements, we would like those projectors to sum up to the identity for each of the hyperedges. When we do so, we recover a set that can be slightly larger than the classical set for certain contextuality scenarios. And it's actually the fact that there exist contextuality scenarios for which there are quantum models that have no classical realization, what we refer to as contextuality. So the fact that there is that gap there is what Koch and Specker realized some years ago in the 60s. And that's what we denote by contextuality. So far so good. So this is a way to describe a situation where we have a system, we perform measurements, obtain outcomes, and we want to study the statistics of those outcomes. Now the question that we ask is, what happens if we have two different such situations? What happens if we have, for instance, Alice and Bob, and each of them has their own systems, their own measurement sets, their own outcomes, their own identifications, and we want to try to understand those two separate systems as just being one. So how, starting from the two individual hypergraphs, can we construct a hypergraph that represents the situation, the joint situation? And of course, there are many different ways that one could think of, composing two different hypergraphs. But one of the properties that we would like for the new hypergraph to have is that this set of probabilistic models allowed on this joint hypergraph satisfies the no signaling principle. That is, that when we take the marginal over whatever outcomes Bob obtains in his share of the state, that the marginal conditional probability distribution for Alice does not depend on his choice of measurement. So that's a property that we would like this new hypergraph to have. And just don't be perhaps misled by this, but this is just an example that I draw where Alice and Bob have two dichotomic measurements each. But what I'm saying holds for any arbitrary contextuality scenario for the parties. And actually, we were not the first ones to ask for this question, and it was answered quite nicely in a different context by Foley and Randall, and they defined their fully Randall product of hypergraphs that actually answers this question. So whenever we want to define a new hypergraph that tells you what is the way to compose those two subsystems, then basically you take the fully Randall product and you obtain what we wanted to begin with. So that's a very wonderful thing. And for instance, here is this very complicated hypergraph is the fully Randall product of those two very simple ones. Note that it's not just the Cartesian product, which is given by these blue sets, but it has something else in there. So now, even though this is really nice, now one can be a bit ambitious and say, well, this is for two systems. What happens if we have more parties involved in the experiment? So what happens if we have three different contextuality scenarios and we want to combine them to form just one? And there we ran into problems because the fully Randall product is not associative. So it depends on where you put the brackets, what is the hypergraph that you obtain in the end. So the now possible question would be, how can we generalize to multipartite situations such a fully random product in a way that the resultant hypergraph, as I mentioned before, allows only for no signaling probabilistic models? And even though one might think that such a constraint is a very strong one, it gives rise to more than one possibility. Actually, we found a hierarchy of products for these hypergraphs, that all of them give rises to different joint hypergraphs. However, they all have the same set of no signaling probabilistic models allowed. So here I just, of course I cannot comment of all the possible ways, but I highlighted 3. So basically the minimal and the maximal products, which are the 2 extremes of this hierarchy of products. And then one that we've got used to referring to as a common product, which is the one that might be a little bit more natural for operational purposes. I unfortunately don't have the time to go in detail on what each of these products is, but the main idea behind it is that for this minimal product, so all of them have the same set of vertices, which is the Cartesian product of the vertex set. They do differ on the hyperedges. So for instance here, the hyperedges of the minimal product set is just the union of all the possible ways of taking a bipartition between one party and the rest. And the rest of the parties, you just take the Cartesian product of the edge set and then fully random with the remaining party. And here, you just take the union of all the possible ways of taking bracketings in the fully random expression. Mm-hmm. And well, for maximal product, it's a little bit more convoluted, but it relies on the notion or on the definition of what a measurement protocol is operationally between all the parties. So if any of you is interested in that, I can comment on it in the coffee break or later. Mm-hmm. So as a mathematician, one could say, well, all of these are equally valid answers because they all give rise to a joint representation of the scenario that have the properties that we want. But then perhaps a physicist could be a bit disappointed because you could have in the back of your mind, well, I would like to believe that nature has one possible way of combining systems and not that there are many ways and it just flips a coin and depending on its mood it decides which way to compose that time. So one could say, well, how about we devise experiment and we compute the statistics and from the statistics of the experiment see, like if we have a quantum system, see which are the correlations that we obtain and then we see if they can belong to each of these joint hypergraphs there. Then is when we run into problems because actually classical and quantum probabilistic models are observationally equivalent. That is, the set of classical and quantum correlations that you can obtain for all these different products are the same. So if you want to rely on an experiment or quantum experiment or classical experiment to tell one from the other, you will never succeed. Mm-hmm. So one possible question is whether this is like some fundamental property of nature and that we could learn something from it, or if it's just coincidence that it just happened that the family or the hierarchy of products that we found out have this particular property. But we still don't really have any intuition about this, so we don't know which of those cases should actually be happening. But what we tried is like, well, how about we probe these different products from a different perspective, like other probabilistic models, which are not this particular one that have this curious property. And that's how we moved on to almost quantum models that actually Marcus was mentioning almost quantum correlations in his talk before. So within this formalism, almost quantum models are defined as follows. So it has a very similar definition than the quantum one, but here we don't demand that the projectors sum up to the identity. So basically, the probabilities that they recover should sum up to the identity. However, the projectors can be subnormalized. So this trivially has quantum correlations as a special case. And here, actually, we were able to find at least one difference. So there exist contextuality scenarios for a tripartite case when the minimal product gives a different set of correlations than the common product. And that, actually, we found it for the simplest example that you can get, which is 2 dichotomic measurements per party. And the way that we signal this difference between the two sets is by testing maximum violations of Bell inequalities. The one that we found it actually this behavior for different inequalities, but the one that I wanted to present here is guess your neighbor's input, where we see that for almost quantum models in the common product scenario, we obtain a maximum value of 1. However, we can go beyond that value for almost quantum models in the minimal product scenario. So this we've observed this behavior for different Bell inequalities. This is a particular one. The reason why I chose this one to present in this talk is because it's clear from this inequality that almost quantum models in the minimum product scenario violate the local orthogonality principle. So now one could argue that, well, since local orthogonality is a principle, what would happen if now we impose the principle ad hoc and do exactly the same, like maximizing the violation of Bell inequalities, imposing this principle to begin with. And surprisingly, when we do that, all the gaps disappear. So not just for this particular inequality, for which it would be trivially the case, since this is a local orthogonality constraint to begin with, but for other Bell inequalities that are not in local orthogonality form, imposing local orthogonality from the outside reduces the gap. And yeah, I have to also say that for all the possible Bell inequalities that we sampled from when we were doing this search, we were not able to pinpoint any difference between the common product scenarios and the maximal product scenarios. So a working conjecture is that perhaps those two scenarios, even though they have different set of hyperedges, they actually give rise to equivalent constraints as far as almost quantum correlations are concerned. So well, it would be up to you to decide, but this could be like a mathematical curiosity or yet another way or another proposal to compose systems. But let me introduce you briefly to the notion of a completion scenario. So a completion scenario basically starts from a hypergraph. So let's take this one as an example, and that's the following. For instance, in this case, we can have an assignment for that green vertex there, the up one there, of value p. And because of the normalization of the probabilities, that implies that this vertex down here has a value of 1 minus p. So for all practical purposes, p, the green one up here and the green one down here, sum up to 1. So they do behave as if they belonged to a measurement to begin with. So if we did that and we included this dashed hyperedge there, then the set of possible general probabilistic models here wouldn't change. So this dashed hyperedge here is what we call a virtual edge. And actually, the way that you construct the completion scenario from a certain contextuality scenario is by including in the edge set all the possible virtual edges. And of course, by definition, the set of probabilistic models allowed in those two hypergraphs is the same. They coincide.
In that example, don't the presence of those two hyperedges at the far right force P to equal 1 minus P?
Well, yeah, in this particular one, yeah.
So then in fact you could draw all such pairs.
Yes, well, exactly. So here you have to, if you want to include all the possible virtual edges, you will have to do all the other. Yes, exactly. This one was a nice example because it gives you the idea of what a virtual edge is. It's perhaps a trivial scenario because it admits only one possible probabilistic model, but I'd rather present something that gives a clear idea of what a virtual edge is, regardless of whether it's an interesting scenario or not.
Sure. You can talk about those two right-hand ones, and then it would still have been
Yeah.
okay, it's fine.
So the curious thing here is that classical and quantum models also have the property. So if you have a classical and quantum assignments in the original hypergraph, then they would also be valid assignments in the completion hypergraph. So one could think, and another property is that the completion, when you have a product of hypergraphs, does not depend on the choice of products. So you take this family of different products that we found, you take the one that you like the most, you use that one to compute the joint scenario, and then when you complete it, you obtain the same thing that you would have if you had chosen any other product. So one possibility or one proposal would be to say, well, perhaps a joint scenario would actually be the completion of all these possible products, given that that thing is invariant. I don't know if there is any physical motivation to do such a thing, but given that we don't even have motivations for the other products to begin with, then this is yet another proposal. Sorry, yeah.
I was going to ask if you were close to that, but then you flashed up the summary.
Yeah. Basically what I tried to argue in this past 15-20 minutes is that within this hypergraph framework for contextuality, there is no unique way to compose the systems when you want to work with multipartite experiments. And however, from the different ways that we studied to try to compose the systems, general models, classical models, and quantum models give no difference, so they're all observationally equivalent. Almost quantum models, on the other hand, do not have that property. So if nature was almost quantum, then perhaps you could devise an experiment to see which is the way that nature prefers to compose systems. However, if actually the local orthogonality principle holds and we are left with almost quantum models that respect this principle, then we still wouldn't have a test because the Bell inequalities that we found so far that witness gaps don't witness those gaps anymore. But now, the fact that all the inequalities that we've studied have this property doesn't mean that that's actually what happens in general. So there could still be the case that there are gaps that local orthogonality might not eliminate. So one possible thing to do is to try to study other multipartite scenarios, other Bell inequalities, and try to see if we find a counterexample to the fact that LO removes the gaps. And also, like I said, everything that I've been saying corresponds to a gap between the minimum and the common product, but we still haven't been able to witness any gaps between com and max. So, or also completion, if we include it as a possible way to combine systems. So it would be actually nice to see if there is a way to tell them apart from the point of view of interesting probabilistic models or not. And last but not least, one of the things that motivates me the most is try to find an intuition or a reason why we should settle for one product and not for another, or try to understand how to understand nature and see which is the way that we should compose these systems to, reveal its behavior. And with that, thank you very much for your attention.
So if you take the free Ramberg product and you add So if you take the initial product, so 3 Randall, and you add the completion procedure, so you get now a product which is associative. No?
I guess so, but you would take the completion.
Yeah. So maybe it means that this is this one which is the good product now.
Oh, okay, yeah, I see your point. Okay, yeah, like. Yeah, that's true. I don't know. I don't really have any physical intuition of why, for instance, that would be the sensible thing to do and not to take the common product, for instance. That's.
Okay.
So by observationally equivalent, you mean that all the nodes are assigned like the same properties in the two guys, even though they don't have
Oh, well, what I mean by observationally equivalent is that they admit the same sets of probabilistic models. Like, if you have a quantum assignment here and you translate it to the other scenario, then that's also a valid quantum assignment there. So you will not have like a quantum assignment on one scenario that is not valid on another scenario, like what you had with the almost quantum models.
things will normalize appropriately.
Yeah, it's like things magically normalize and satisfy all the properties that you would expect.
Okay, let's thank Anna again.